Hi everyone, we are back and we are going to go through our Pset 6 solution videos. So I'm playing rock, paper, scissors, lizard Spock for 10,000 rounds, claimed to be perfectly random. So we have some observed values, we have some expecteds. These are our observes. Boom, 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 boom. Expected should just be 10,000 divided by 1, 2, 3, 1, 2, 3, 4, 5, 1, 2, 3. Ooh. Rock, paper, scissors, lizard, Spock. Paper. 1. Rock, paper. Ooh, I'm missing a scissors value. Ooh, that's not fun. But let's just say again, if I'm truly random, let's say I didn't decide to do scissors. So it's just this divided by 4. If you want to, you can kind of say, you can give a value of 0 for 5. I would definitely accept that solution. So what we have to do, we're going to have to pull this value up. Observed, expected. We're going to have to do a chi-squared calculation. So let's get at it. I'm using this notebook. So my observed values are going to be as follows. Let's go over here. Here we go. There. My observed, let's say it's equal to 2768, 800, 4,000, and then 2522. My expected is just going to be equal to a fourth, a fourth, a fourth, a fourth, all that multiplied by 10,000. Observe minus expected, 2,084. So our chi-squared experimental is equal to 2,084. So basically, we'll know what is our chi-squared theoretical. Well, our chi-squared theoretical is going to be 10% 0.1. How many expected values? 1, 2, 3, 4. So it's going to be nu minus is equal to k. Nu is equal to k minus 1 minus r. R is 0 because we're not looking at any fitting parameters. K is equal to 4, so 3. Let's look at our chi-square table, even though we don't really need to. What is it? 10% significance. So 0.1, 3, 6.251. If we look at our chi-squared, 6.251, 2,000 is way over here. Reject, P is less than alpha. Excellent. Bought some thermocouples that claim to measure room temperature. So let's actually go ahead. Temperature. So I'm going to shift enter this, shift enter this. We found some observed values. So I'm going to list out the observed values as we read. So I'm going to go down to here. Actually, I'm going to go right here. All right. So my observed, actually, I'm going to quit the kernel, quit everything right now. Oh, I don't want to quit everything because then it's going to mess up. I'll just be careful. Observed value is equal to 10 measurements between that, 15 between that, 1,500, 5,000 between and then 7,000 measurements. So took 5,000 measurements and found 10 measurements less than this, 15 and 7,000 measurements. I mean, we'll just have fun with it anyways. Should be able to have that, but let's confirm with our answer. So those are observed. Expected, mean of 298, a standard deviation of 1. So now 10 measurements less than 297, and we're going to go from minus infinity and then to that z value, and our n is going to be equal to 5,000 measurements. So that's our expected 1. Our expected 2, 15 more than, so basically we're going to go 301 to infinity, and beyond. I can never stop myself from making that joke. That's our expected 2. Our expected 3 is between 297 and 298. So 297, actually not 298, 299. 297, 299. And then expected 4 is going to be 297, 299, 296, 302. Expected 5, 296, 302, less than 300. 300, you should do minus infinity. And there we go. So we have 5. So in this problem now, significance, is it normally distributed at significance level 1%? So our chi-squared will be 0.01. Our nu is equal to k, which in this instance is 5, minus 1 minus r. R in this instance is 2 because of our fitting parameters mu and our standard deviation. So that is going to be 5 minus 3, which is going to be 2. We can look at our value here. 0.01 and a nu of 2, which is 9.21. There we go. And then what's our chi-squared experimental? It better be a reject. Observed minus expected. And actually, let's do our observed list. Looks good here. Our expected list, put it in here. Yeah, insane number. But it makes sense because of that value. So that is a big old reject. P is less than alpha. Fantastic. I'm just going to try to erase this. Get this off the screen. There we go. Tough to erase all that. All right, propagation of error problem. I love these. So let's go ahead. I'm going to quit the kernel now because we know we're just going to be doing our usual. So we have a fundamental function, sigf is equal to 3 times f times L divided by 2 times b times d squared. So we have a resolution or an uncertainty in the force, which is going to be equal to 1 times 10 to the minus 3. We're going to also have ruler, centimeter thick mark, so some uncertainty in the length, which is equal to 1 times 10 to the minus 2. Uncertainty in B, which is equal to uncertainty in L. Uncertainty in D, which is equal to uncertainty in L. And that should be it. Good. Number of force measurements is equal to 33. XF is equal to 115 times 10 to the 3. SF is equal to 2.1 times 10 to the 3. The width of the beam, which is B, so number of B measurements is equal to 25. XB is equal to 17 times 10 to the minus 2. And SB is equal to 3 times 10 to the minus 3. And then number of L measurements is equal to 11. XL is equal to 0.2. And SL is equal to, average length was 2.3. And then the standard deviation was 0.2. Fantastic. So there is uncertainty in each of the variables. So my bias is going to be equal to square root. And actually, I need to. So I'm going to have derivative sig df is equal to derivative of sig f with respect to f. And then I'm going to shift enter these because I want to see these. So that's f. I'm also going to have an L and an L. Looks good. I also am going to have with respect to B, and with respect to D. Once I see that this is working, I'm just gonna, I'll hide that. I'll suppress the output just with my semicolon. Good. Always good to double check your partial derivatives. Bias is equal to square root of, so d sig df times uncertainty in f divided by sig f. I'm going to square that, I'm going to do a plus, and now I'm going to copy and paste this 3 more times. 1, 2, 3, because UF, UL, make sure that, again, don't rush. D, mu D, mu dB, ub. Shift enter, I'm going to do slash dot x, or actually not x, b goes to xb, d goes to, now the nominal value of thickness was 5.7 times 10 to the minus 2, f goes to xf, and then l goes to xl. And there we go. So that is our uncertainty for this particular problem. Fantastic. Let me just double checking one thing here. Make sure I got the value correctly done here. Let's see. 1 millinewton. Dimensions. 1 times 10 to the minus 2. X of f. 1 5 times 10 to the 3. I'm just double checking for these nominal values. The width of the beam was 17 times 10 to the minus 2 XL. The beam was 2.3. Yep, looks to be correct here. And the process is pretty solid. All right, so precision air. The precision air that we get now, I believe so. I may have had a little adjustment there. My precision air in force is going to be equal to, now I actually have to find those values. So how many times did we measure? We measured in the number of force measurements, basically an infinite number of times. It looks like we're looking at 1% significance, so need to be 0.1, so 0.005, because it's alpha over 2. So I need to do my t value of 0.005, actually 0.05, so 1.645. So 1.645 times my s of f divided by square root of n of f. And I'm going to pop that here, and I'm going to divide that by x of f. Excellent. And let's go ahead. That's my p of f. I can now do my p of b. So how many times do we measure b? Measured B 25 times, so we need to do 0.05 times 20, or 0.05 and 24, so that's 1.711 equals 1.711 S of B, N of B, X of B. There we go. And then finally, we're going to do our precision air in what? Length. L, which is going to be, we did it 11 times, so 0.0510, which is going to be 1.812. And S of L, N of L, and B of L. Or not B of L. And now we're going to do square root of my bias squared plus my precision in F squared plus my precision in B squared plus my precision in L squared. And That's going to be our uncertainty. How would we shrink this? If we only just use a micrometer, look at this. This is always so cool to me. So if I used a micrometer, so I can look at how this changes things. 0.355. Really nice. So now, if we just run the rest of these, so we can see, look at the change in our uncertainty now. And now it's completely dominated by the length. So the length is a harder one to fix because you either need more measurements or you need to kind of fix that standard deviation. But that is it. So how would I redesign it? Again, just like we saw, use a micrometer. And we would have fixed a lot of issues. Thanks, and I'll see you all next time.